Hi guys, hope you're having a good evening. Welcome to the live today that we're going to go through some exam questions on energy and energy transfers and some specific heat capacity. So with these topics, I'll also be doing a live class on Sunday to go through these. So we'll be going through the content in some more detail as well, going through the notes and then consolidating that knowledge with some questions at the end. So if you want to go through the actual notes on the topic, then join our live on Sunday where we will go through it in more detail. So without further ado, I will go to physics and I will go to changes in energy. So this will be with different types of energy transfer and the equations related to them. So I'm going to write these out. Obviously, there's a few calculation questions here, so I'll talk through them. If anyone has any questions, drop them in the chat, and I'll answer them as we go. In addition to that, if you have the answers and you know the answers, feel free to put them in the chat as well, and we can check and make sure that that's right. Cool. So, first question. Also, let me know if it's not zoomed in enough. I can zoom in a bit. But the first question says, a trampoline is made from a sheet of material held in place by stretched springs. The figure below shows a child on a trampoline. So he's jumping on this material, and you can see as they stand on it, the springs are stretched. When the child is at position A, each trampoline spring is stretched by 0.056 meters. So I'll just underline the key numbers as we go. So we've got a stretch of 0.056 meters. The elastic potential energy of each spring is 4.9 joules. So it says when the child is at position B, so on the left-hand side now, the elastic potential energy of each spring increases to 8.1 joules. So it's asking us to calculate the extension of each spring when the child is at position B. So to do that, we're going to need to know what the elastic potential energy equation is. So you can use the equation sheet as it says, but the equation will be, if I go back to this, sorry, it will be EPE, so elastic potential energy for short, is half times the spring constant, which is a letter K, times the extension squared. So extension denoted by the letter X. So with position A, we can see they've told us that the elastic potential energy in the spring is 4.9 joules. We're also told, as I've underlined, that this stretch in the spring is 0.056 meters. So that is your extension. Hi Jordy, sorry. Thank you for letting me know. I will zoom in a bit. Hopefully that's a bit better for you. Try and go a little bit more. Hopefully that's all right. Cool. Okay, so as I said, we've got 4.9 joules as the elastic potential energy, and the extension is 0.056 meters. So I'm going to do 4.9 equals half times the spring constant, which we don't know yet, times by 0.056 squared. Yeah. Now, we want to rearrange this to end up with a value for K. So, first thing we need to do, I'm going to say, is times both sides by 2. That way, we get rid of this half here. So, it'll be 2 times 4.9 equals K times 0.056 squared. Yeah, and then once I've got that, I want to get K on its own, so I would divide by the 0.056 squared. So K equals 2 times 4.9 over 0.056 squared. And that will give me a spring constant of 3,125 newtons per meter. Yeah. Joanne, yep, so we do live lessons every week. We do them on a Sunday, and it will be 2 of the 3 sciences going through the content in the week on the Sundays, and then in the weekdays on Monday and Wednesday we have lives like I'm doing now, where we'll go through exam questions on some topics. So today's, for example, is on energy, which is what we're covering at the moment. Chicken, what app is this? This is flashrevisionlab.com. I'll go back and show you the website quickly again after this question is done. Or actually, you know what? I'll show you now. If I zoom out a bit. So flashrevisionlab.com. You've got all notes for all 3 sciences. That's biology, chemistry, and physics. So if you go to the menu on the right here, you can see for combined and triple, we have notes for all 3 sciences. So that's why I'm covering physics at the moment. And you've got all the topics laid out here with a menu going through topic by topic, with notes showing videos going through the notes, as well as written notes as well to go by. Yeah. So yep, check it out for sure. It's a great tool to help you revise for your exams. Now is the perfect time to start using it as we get closer to exams. Check out the videos, try the questions, use the notes, and you should subscribe and join the lives as well, so you can get taught by our tutors as well. The website is free, absolutely. Yes, all the notes content I'm showing you today, this is all free. So yeah, just sign up, and you can also track your progress, and you can see this progress part at the top here. You'll be able to track your progress on there. No problem. So I think I saw some other questions. 1 second. So Zach, will this equation be given to us in the formula sheet? Yes, as you can see in this question. If I zoom in again, sorry. It says use the physics equation sheet, so you will be given the equation. Okay, so where we ended off, we had that the spring constant K was 3125 newtons per meter. So now we have the spring constant. They want us to calculate the extension at position B. So if I go back to the question, at position B, the elastic potential energy of each spring increases to 8.1 joules. Yeah, so now we know K is 3125. It's still the same because it's the same springs, but the energy this time is 8.1 joules. Someone asked, is this triple? No, it's not triple science. This is combined. So it's at near the start of the energy topic in topic 1. Bronze Lucy, this is flashrevisionlab.com. So I think my moderators will drop the website as a chat here. So just click on the link, sign up, and register, and you'll get access to all of this. So if E is 8.1, K is 3125, I'll again put the equation E equals half times K times x squared. So half times spring constant times extension squared, and I'll substitute the numbers. So that is 8.1 equals a half times, now our spring constant, which we know is 3125, times by x squared. So now we just want to have x squared on its own, so we'll divide these two numbers and bring them over to the left-hand side. So that's x squared equals 8.1 over half times 3125. And then to get x, we will then need to square root that whole thing. Yes, square root of 8.1 over a half times 3125. And that gives us a value of 0.072 meters. And that is for a total of 5 marks. Sorry, someone asked earlier. It was just off the screen. Apologies. So that is for 5 marks. Yeah, so quite a big question, but you're just using the same equation twice, just in 2 different ways. Yeah. So, and on top of that, as I said, if the equation is given to you in the formula sheet, so it's just applying the equation in this question. Yeah. Cool. Moving on then. The diagram below shows a lift near the bottom of a building. The lift is attached by a cable to a counterweight. An electric motor moves the lift, and the lift is moving up. So they've labelled everything that you can see here. So they mentioned the pulley in the question, the counterweight, the electric motor that's causing it to lift, and the cable, obviously that's attached to the lift. Calculate the change in gravitational potential energy of the lift when it moves up 4 meters. And they've given us that the mass of the lift is 1300 kilograms and the gravitational field strength is 9.8 newtons per kilogram. In this question, they've actually given us the equation as well, which is why you can see as a result of that, the question is actually only worth 2 marks, because they've already told us the equation as well. So it's just a matter of substituting in the numbers that they've given us. So gravitational potential energy equals, so if I put GPE equals, and the mass, which is the 1300 kilograms, times by the gravitational field strength, which is your 9.8, multiplied by your height, which is the 4 meters. So don't know if anyone's done it, they can drop a message in the chat. 50,960 I've got, that is correct, Louis. So good. 50,960 joules. Yeah, they've given us the unit already in the question, so there we are. 2 marks. Easy. Let's go another one. So, kangaroos are large animals that travel by jumping. The photograph below shows a kangaroo. Each leg of a kangaroo has a tendon connected to a muscle. Each tendon can be modelled as a spring. When a jumping kangaroo lands on the ground, the tendons stretch. A kangaroo has a maximum gravitational potential energy during one jump of 770 joules. When the kangaroo lands on the ground, 14% of the maximum gravitational potential energy is transferred to elastic potential energy in one tendon. The tendon has an unstretched length of 35 centimeters. When the kangaroo lands on the ground, the tendon stretches to a length of 42 centimeters. Calculate the spring constant of the tendon. That's so hard, I see. Well, I can see why you say that. Obviously, it's a lot of words. Yeah, it's plenty to read. But when we break this down, it's a 5-mark question, so it's worth a fair few marks as well. But it's just breaking it down into steps. Yeah, and that's what will make it hopefully much easier. So let's take a look. A lot of wording in there. Yeah, so we just need to highlight the key terms. So they've talked about a GPE of 770, so that's important. Yeah, they've also spoken about 14%, so it's about the of the energy that's used is transferred to elastic potential energy. Advanced mindset, this topic is energy, so particularly energy changes in systems. So it's chapter 1 in AQA. So, so we've got the gravitational potential energy, we've got 14%, which is it's actually a reference to efficiency. Yeah, so we're going to come on to that. The tendon has an unstretched length of 35 centimeters, so that's an original length. And then it's got, when the kangaroo lands, it reaches a length of 42, so that's the final length. Yeah. So, calculate the spring constant of the tendon. So, to work that out, we need, again, the equation for elastic potential energy. That's where we find spring constant. So, I will put E equals half kx squared. Yeah, what I referred to before. Half times spring constant times extension squared. Now, let's see what we know from the question. So, they've given us a gravitational potential energy of 770, not elastic potential energy. So apologies, I will put EPE here, just to clarify this is the equation for elastic potential. Geordie, will we be going through this topic on Sunday? Yes, we will. So at 6:10 on Sunday, we will be doing this topic of energy. And also before that, we will also have a chemistry lesson on atomic structure as well. I can see a question there. I thought it's E equals KE. Not quite, no, that's for force. So that's force equals, I'll put it down here, force equals spring constant times extension. So F equals KX, or, yeah. And yeah, I've used X, you can use E as well, that's correct. Yeah, sorry, so I can see you've changed what you mean. So yes, E for extension or X for extension, either is okay. Yeah. So if this is the equation, we don't know the elastic potential energy, we need to work it out because they've told us 770 joules is gravitational potential and 14% of that is transferred to this EPE. So we will need to do 770 times by 40. Actually, before I do that, I'll show why I'm doing this, because I mentioned it's to do with efficiency. Efficiency is another equation that you can get from your formula sheet, which is useful energy output over total energy input. So in this case, we know, and you can times that by 100 to give you a percentage. Yeah, so times by 100, if I move that, times that by 100, I can't fit it in there, that's why, sorry about that. There we go, times by 100. Yeah, so if I put the efficiency as 14%, that equals a useful energy, so in this case the EPE that we don't know, over the gravitational potential energy, which is 770, times by 100. So therefore this elastic potential energy will be 14 times the 770, because I'm going to bring it up, divided by 100. Yeah. So that is going to give you a value for the energy of 107.8 joules. So now we have the EPE, 107.8 is our EPE. It's not, it's not input over output, it's output over input, because you'll always have more input energy going in than you would have output coming out, isn't it? So if I put in 100 joules of energy, I'm not then going to have 105 joules of energy coming out. It's always going to at maximum be 100. So the input is always on the bottom. So 107.8 joules, we want the spring constant, that's the question, we don't know it, so we don't know K, so we need the extension X. Yeah? So to find the extension X, we need to look at the lengths that I've put here, 35 centimeters when it's unstretched, and then it stretches to 42 centimeters. So to find X, we just need to do the difference between them, so I'm just going to do that up here. X equals 42 centimeters minus 35, which is 7 centimeters. Yeah. Another thing though to spot, which is where exactly Lois mentioned it, because a standard unit for distance needs to be used in this equation, that is in meters. So I need to do 7 divided by 100 to convert it into meters, which is 0.07 meters. Yeah. So putting that all in this equation, we have the energy, which is 107.8 equals a half times the spring constant times 0.07 squared. Earlier I showed just in the couple of questions ago to convert or to rearrange for this, we need to move both of these numbers, the half and the 0.07 squared, over to the left hand side. So it would be K equals 107.8 over a half times 0.07 squared. Yeah. And putting that together, that will give you an answer of 44,000 newtons per meter. If you put it in your calculator, there will be a lot more numbers than that. It'll probably be 44 and a lot more digits. The reason I've chosen 44 is because of the number of significant figures in the question. Yeah, so whatever they give you in the question, you should stick to that in your significant figures for your answer. So 770 is 2 significant figures, 14 is 2 significant figures, and 35 is 2 significant figures. Yeah, okay, so I can see that you're lost, so what I'll do is I'll go back and show you this step by step. So this is the equation for elastic potential energy. Yeah, the reason I brought that up is because the question has asked me to calculate the spring constant. Yeah, so to find spring constant, the only equation we know that does that is this one, half K E squared, as you mentioned. Then we need to look at what terms we need. Yeah, we want to find this K. Yeah, so that means to find it, we need to know the other two, elastic potential energy and E squared. Yeah, so therefore underneath here, I use the equation for efficiency to then calculate what the elastic potential energy is, because they've only given us 770. Yeah. Following that, I used that energy, and then I worked out the extension, which was 42 minus 35 because of the two lengths they gave us here. So that's where the 7 centimeters came from. Yeah. And then converting that into meters, so 0.07 meters. Yeah. Following that, I then put those numbers into this equation now. See, so I've got everything except k. I've got 107.8 equals a half times k times 0.07. So k is here. From there, I rearranged for k. So k equals this 107.8, which is on the left-hand side, and I moved both of these to the left-hand side. So divide by a half and divide by 0.07 squared. So that's why it's all of that is on the bottom, half times 0.07 squared. And that is what gives me the answer of 44,000 if you put that in your calculator. Ed, the half mv squared equation is for kinetic energy. Constanza, this is for paper 1. This is paper 1. Cool. So, let's look at another one then. Hopefully it will make a bit more sense. So, Dania, generator effect. In this class, I won't, unfortunately, because I'm covering energy specifically, but we will be doing classes and lives later on in the next few weeks, and that will be one of the topics that we cover. You mentioned why efficiency doesn't come in. I don't know, I think you've put O after, but the reason is because of the 770 joules is for gravitational potential energy. And they've told us the percentage of that maximum gravitational potential energy is converted into this. Yeah, so we know how much of this energy becomes this. That's why I've used it. So let's move on to this question. Mimi, yes, this is GCSE. Let's answer the live. Do we have a live timetable to see when you go live and what you do in that live? Yes, sure. So I will go to that now. If I zoom out a little bit, I can show you. So if I go to the home page, I'll go to the top right here and I'll go to live classes. Yeah. And if you scroll down, at the bottom of the screen, you'll find a list of all the classes that are happening. So this is both for what I'm doing right now, so on TikTok, and also on YouTube on the weekends. So that will be paid classes that happen on Sundays, such as the ones at the top here, these content masterclasses. Yeah, and you can see the dates they're happening, the duration, and also the start times. Yeah. So this website is flashrevisionlab.com. Yeah, so yeah, definitely please go check it out, sign up, subscribe, and you'll get access to everything, not just everything on the website, but also the live classes that we do on the Sundays. Okay, let's go back. So if I go to combined. Let's look at one more question here. Question 4. Okay. So hopefully you can see that better again. In a sport called far leaping, an athlete uses a long pole to cross a river. Figure 1 shows an athlete far leaping. Figure 2 shows the athlete in different stages of far leaping. The pole falls over from position C. The athlete lets go of the pole and lands at position D. The change in height of the athlete between position C and D is 3 meters. The mass of the athlete is 50 kilograms and the gravitational field strength is 9.8 newtons per kilogram. They say calculate the change in gravitational potential energy of the athlete between positions C and D. So, and they've also given us the equation there in this case. Yeah, so we want to find the gravitational potential energy as it says here. So we just substitute in the relevant numbers. Yeah, so GPE equals mass, which is the 50 kilograms of the athlete, multiplied by the gravitational field strength, which is 9.8 newtons per kilogram, multiplied by the change in height, which they tell you the change in height between C and D is 3 meters, so times by 3. So 50 times 9.8 times 3. Has anyone done it? If not, tell you the answer is 1,470 joules. But again, here's an example. You can give that as an answer, but also the most significant figures they give in the question with all these numbers is two significant figures, right? 1, 2, 1, 2, 1, 2. So you can also give your answer to two significant figures, which is rounding this to 1,500. Cool. Next question. The kinetic energy of the athlete at position D is 1,600 joules. The mass of the athlete is 50 kilograms. Calculate the speed of the athlete at position D. And again, they've given us the equation here, so it makes it a bit easier. Yeah. And the last thing also, they've said choose a unit from the box. So again, this is a bit of a substitution exercise because we are given what we need to work out. So speed, I'm just going to put V for short. And this is the square root of 2 times the kinetic energy, which they've given as 1,600 joules, over the mass, which they've given as 50 kilograms. So putting that into your calculator, you'll get a value of 8. Now for speed, what would the unit for speed be? Anyone in the chat? Mimi, good? 8. Can you tell me the units as well? Alfie, good to hear. Nice to see that it's helping you. Hopefully it continues that way. Geordie, meters per second. Perfect. Thank you very much. Yeah, so speed is meters per second. If we go through, these are for different units. Joules per second is actually for power, and joules per kilogram is a measure of specific latent heat. So neither of those are for speed. So Amna, yep, correct. Meters per second. There you go. 8 meters per second. Awesome. So I want to move on just to try a question on specific heat capacity. So I'm going to go to this topic over here for specific heat capacity. As I mentioned, you can go through the notes, check out the video. You can see here, press play, and it will go through things in the notes, but obviously with a bit more detail, and also questions. So there's checkpoints that take place here, as you can see in the dots, and they will test you with questions as you're going through the content to make sure that you're understanding as you go along. So it's really useful, guys. Definitely go and check it out. And you can see all the notes here. So with examples as well. So you can always refer to these, even with the exam questions I'm doing now as I go to the next tab. You can always flick back to the notes and check if you're stuck. Yeah, so it's a great tool. So if I zoom up a bit. A student investigated how the temperature of water changed as it was heated. The figure below shows some of the apparatus used. So you can see a power supply, thermometer, an electric heater submerged in water in a beaker. The student switched the heater on and then recorded the temperature of the water every 5 minutes. The table below shows the results. So you can see the time recorded every 5 minutes, along with the several repeated tests they've done, and then a calculated mean of the temperature in degrees C. The first question asks, what was the resolution of the thermometer used in the investigation, based on the table above? M asked, what app is this? This is a website and it's called flashrevisionlab.com. So everything I'm doing here, you can see on there, sign up and you'll get everything for free. So check it out. So does anyone have any idea on what the precision would be, the resolution that they've mentioned? What would the resolution of this thermometer be? So resolution often refers to how accurately the measurement is being given to. So like how accurate you can measure based on the equipment that's given. Yeah, so Mimi, I think you've got it, because you can look here. The most accurate it can go to is every 1 degree. Yeah, it won't go to 0.5 or 0.1 of a degree. It will only go to 1 degree. Yeah, that's the most precise it will give. So the answer in this case is 1 degree. Correct. So we'll give that a tick. And then it says calculate the mean in the table above. So I can see someone else has given the number already. A bit of maths here. So you said 45. Now that would not quite be right, because you need to take an average of the 3 values. So there's 3 test values they've given here, so you need to sum them up and divide by the total numbers you've used. So in this case, 42 plus 45 plus 45, and divide that by 3, because that's 3 values. So if you put that in your calculator, you'd actually get a value of 44 degrees. 56 wouldn't be correct, Mr. Nobody, because that's in the wrong section of the table. We're looking at value x, the mean. So that's referring to these 3 values here. Mimi, yes, this is paper 1, correct. Then it says, draw a ring around the anomalous result in the table above. So an anomalous result is a number that kind of sticks out from the rest. It doesn't fit the trend. It's quite far off, what we call an outlier. It doesn't really follow the other measurements that we've got. So I'd go row by row and look at which ones are close and which one isn't. So first row, they're all the same. It's fine. These are all 1 or 2 degrees apart. That's okay. The maximum 3 degrees apart. That's fine. And then in the last row, you can see these 2 measurements are 2 degrees apart, but the 64 is 10 degrees or 8 degrees away from these, so it's the largest difference. So correct 64 would be the anomalous result. What should the student have done with the anomalous result? So when you're doing an experiment, what would you do when you have an anomalous result? Dania, by only doing your revision notes and exam questions, is it possible to get a 9 purely with your website? Yes, so that's using the website for checking the notes and also trying exam questions. It's all about getting the knowledge and then also practicing it. So it's applying that knowledge is really important. So you need to go through the notes and then attempt the questions. And if you can do the exam questions without help, get the answers right, then you're as prepared as you can be for your exams. Why is 64 the anomalous result, Mimi? Because as I was mentioning, the which one is in each row, which one is not similar to the other measurements, and that is 64 in this row, because it's these two. Every single result you see in each row are close together, if not exactly the same. So you're expecting when you record, you should get a similar value every time you repeat an experiment. But here for 15 minutes, when they repeat test 1, 2, and 3, this is quite far off the other 2. And that is why 64 is the correct answer for the anomalous result. So what should the student have done with the anomalous result? I don't think anyone's mentioned it in the chat. Apologies if I've missed it. The key thing is essentially not to use it. So not use it or not use it to calculate the mean. So do not use it to calculate the mean. Because it will affect your results. So you don't want it to have a wrong impact on your results. Ignore it. Sorry, I realize some other people have said that as well. Correct. Ignore it is the right answer. Give 2 ways to reduce the energy transfer from the apparatus to the surroundings. So how would you reduce the energy transfer from this apparatus here to stop the heat escaping from this water, from the electric heater heating up the water? Think of the name of something that we can use to keep something warm. Yes, an insulating material around the beaker. Very good. So we could insulate it around here like this. Good. So insulate the beaker would be one answer. So that stops the heat from escaping from the beaker and the sides of the beaker. But then what about up here? It's open to the air. Yes, Andrea. To cover it off. We want to cover it off so heat doesn't escape from the top through the air. So we would say place a lid on top of the beaker. Good. And then question F: the water in the beaker has a mass of 0.2 kilograms. So I'll underline as we go. The temperature increase of the water was 33 degrees C. The specific heat capacity of water equals 4,200 joules per kilogram degree Celsius. Calculate the change in thermal energy of the water. And again, they've given you the equation this time. Change in thermal energy equals mass times specific heat capacity times the temperature change. And again, and as we saw in a question earlier, it says to choose the correct unit to give us your answer. So again, this looks like we just substitute the numbers in. So we will put energy, I'm going to put E equals, so we've got mass, which is given at the top, 0.2, multiplied by the specific heat capacity, which is the 4,200, which they've given us, multiplied by, it says temperature change. So in this case, they've talked about a temperature increase. So that is your temperature change, which is 33 degrees C. So putting that together, I don't know if anyone's worked that out, 0.2 times 4,200 times 33, that is equal to 27,720 joules. I've given that away. The question did ask, what is the unit as well? It says change in thermal energy. So energy is the clue there, which is why it's joules. Yeah? Degrees C is for temperature, centimeters cubed is volume, and kilograms is mass. So the correct unit is joules. And the last question, explain what happens to the mass of the water in the beaker during a test. Now, it's 2 marks. Yeah? So what they're looking for is what happens and explain. So what happens and why. So 1 mark for what happens and another mark for why it happens. So does anyone have any idea? If there's water in the beaker and we're heating it up, what's going to happen to the amount of water or the mass of the water and why? As we heat something up, especially when we heat water, like when we heat it in a kettle, what happens to the water? Anyone have any ideas? Tanya, exactly. Yeah, so people have said decreases. Yeah, so perfect. Got a high there. Hope you're doing good. So the answer is that the mass of the water decreases. For 1 mark. And this is because the water has evaporated. Okay. Nice. The lesson yesterday was very good. So, okay, yeah, glad to hear it. Very good. And obviously you've got a pro subscription, so look forward to seeing you in the future lessons as well. Nice. So I think that's a good place to leave it for today. Thanks, guys, for joining the live. It's good to see some interaction in the chat, answering the questions. Again, like I said, if you're finding this a bit tricky, obviously some of the questions I went through were quite hard. So yeah, come along, sign up and subscribe to our live classes, which are on Sundays, where we'll go into these with the notes first and go through the notes and really consolidate that knowledge before we try some questions. Yeah, so then next time we do it, hopefully it will be much clearer to you. But keep going, guys. Revise hard. It's the start now to really get your revision in order as you get closer to exams. Danya, thanks. It's good to hear that you found a good revision. Thanks for joining, and we'll see you for our next live class, which is on Wednesday, which will be exam questions on atomic structure. So look forward to seeing you then. Thank you very much, guys. Do you have any tips? Yeah, I would say the key thing always in terms of method for revision is just going through notes. Either you can make your own notes as well, but in this case, if you have this website, I think the notes are great. Follow the notes and then try questions. Yeah, it's always about trying questions is the most important thing. The more questions you try, the more different types of problems you'll face. So I always say trying loads of different exam questions is the best thing you can do. But yeah, great, guys. Thanks for taking part, and see you soon.